Hello, students. This is Mr. Ezra. Today we are going to talk about how to find rational and irrational zeros using a combination of your graphing calculator, synthetic division, and the quadratic formula. So let's get all those tools in our toolbox and get to work. First, let's review how to solve a quadratic equation using the quadratic formula. This is something that we talked about earlier this year and that you've seen in previous classes, I think. But just to review very quickly, the quadratic formula is something you're expected to know at this point in high school. It's x equals negative b plus or minus the square root of b squared minus 4ac, all of that over 2a. We talked earlier about how to sing a song to remember it. There's the story about the negative boy that you can try to remember, but you just got to know this and use it in some cases when you're solving a quadratic that requires it. When you're simplifying with the quadratic formula, the first thing that you want to do is make sure that every time you plug a variable into the quadratic formula, you use parentheses. This is especially important if the thing that you're plugging in is negative, because it can change the answer in your calculator if you're using your calculator to help you. If you put a negative squared without the parentheses, you could end up getting the wrong answer and know what you're doing, but still get it wrong. I tend to kind of like simplify the pieces. I solve the discriminant. I deal with the negative b on the top left of the quadratic formula, and I go ahead and multiply the 2 times a, and just kind of get those 3 pieces simplified as much as I can. I then split up the fractions and then try to simplify each fraction, which sometimes includes simplifying a radical and sometimes does not. Sometimes it includes dealing with imaginary numbers and sometimes it does not. So here are some quadratics that I've already kind of solved, just to kind of review this with you. When I'm looking at this quadratic, x squared plus 4x minus 6, I notice that my a is going to be positive 1 because that's the leading coefficient. My b is going to be 4 because positive 4x means that the b term is 4, or the b coefficient is 4. And then my c term is negative 6. Remember, the sign in front of it stays with it when you think of it as a, b, and c. And I plug those things into the quadratic formula. Negative b is negative 4 plus or minus the square root of b squared minus 4 times a, which is 1, times c, which is negative 6, all over 2 times a, which is 2 times 1. And as I said before, I simplify the top left. Negative 4 is going to stay negative 4. 4 squared minus 4 times 1 times negative 6 is 40. And 2 times 1 is 2. Now, I kind of did two things at once here. I split up the negative 4 over 2 plus or minus the square root of 40 over 2. But as I was doing that, I also went ahead and simplified this radical. So 40 can be expressed as the square root of, or the square root of 40 can be expressed as the square root of 4 times the square root of 10. Well, the square root of 4 is 2, so I can simplify that part of it and pull that 2 out from under the radical, leave me with 2 root 10. I then need to simplify both of these fractions as if I can. Please remember that anything under a radical cannot reduce as a fraction with the denominator unless it's also a radical. So things that are not under a square root sign can reduce, like the 2 and the 2 here, and the negative 4 and the 2 there can reduce to be negative 2 and positive 1. But the 10 is stuck. Unless there was a radical in the bottom, we can't do anything with it. So we end up with negative 2 plus or minus root 10 as our solution. Remember that this is two solutions. It's really negative 2 plus root 10 and negative 2 minus root 10. And these two solutions happen to be irrational because of the square root of 10, since we can't simplify it any further. So we just kind of have to leave it with the root as part of the answer. If you put it in your calculator, you'll get a decimal approximation that you can get, a few places past the decimal. You can get pretty close. You can approximate the value, but there's no way to get the exact value because it is irrational. Another example really quickly. This time I plugged in an a of 2, a b of negative 5, and a c of negative 17. Remember, I said when you plug something in, to use parentheses, and that is important, especially when you have a negative like negative 5 or negative 17, because in this case, negative 5 squared without the parentheses would give us the wrong discriminant. We don't want that. When we put it around this guy here, the negative 17, it lets us know that we're multiplying 4 times 2 times negative 17, and it's not subtraction there. The only subtraction is in front of the 4. So just be careful when you plug things in. Simplify the top left, 5. Simplify the discriminant, 161, and the denominator, 2 times 2 is 4. When I split this fraction up, I could not reduce 161. I didn't have any factors that were perfect squares that I could reduce it. And 5 over 4 does not reduce, so I was stuck with this answer. Remember, this is really two answers, 5 over 4 plus root 161 over 4 and 5 over 4 minus root 161 over 4. So we've kind of reviewed the quadratic formula. Let's get into some actual working with polynomials that are a little bit larger and seeing if we can use this to solve them. Remember, the idea here is some of our solutions are going to be integers. Some are going to be rational numbers that are not integers, that are like fractions or decimals, that either have a repeating pattern or terminate if they're a decimal. And some will be irrational and even imaginary. Like we can have all different types of solutions to these polynomials. So how do you find the x-intercepts of a polynomial equation that will not factor when it just won't work? Well, we are going to use a tool today, and we're going to use our graphing calculator to help find some ones that are rational, that are good. And after we find those, we'll use synthetic division to find a few more. Okay, irrational roots are going to occur when the polynomial after synthetic division cannot be factored. You try to factor it, you're just not able to. So you've got to get the quadratic, you got to get it down to a quadratic. And then in this case, you might need the quadratic formula to solve it. There are other ways to solve quadratics, as you've learned. There's completing the square, there's the square root method. So you don't have to use the quadratic formula every time, but it's the go-to when you can't find another way, because it always works. So here's our example. I'm going to pull up my graphing calculator here. So what if it doesn't factor to begin with, or you just aren't sure? Okay, so the first thing that we're going to do is we're going to find a root using our calculator. And we talked about this in class the other day if you were there. You want to go to y equals, and you want to type in the function. In this case, I've already typed in x to the fourth power plus 3x to the third power minus 5x squared minus 15x. And just as a review, remember your x button is right here. This is your variable button. This is the one that you press when you want to put an x in. When you want to raise something to a power, you use this rooftop or caret symbol here. So that means raise to. If you have a newer version of the operating system on your calculator, it'll pop you up into the exponent. It'll actually look like an exponent on your calculator screen, and you need to right arrow over to get out of that exponent before you do plus 3 raised to the third and then arrow over again. Now, I use a different thing for x squared here. There actually is an x squared button, but you have to hit x first, and then this raises it to the second power. You could use the raise to second power just like you did for the fourth power and third power, and that would be fine. Anyway, I get this typed in. Now, remember we said in class, if you were there, that when you zoom, probably what you want to start with is zoom standard. It goes from -10 to +10 on both axes. And what we want to know here is, where does it cross the x-axis? Now, on my computer screen here, this looks kind of small, and I want to zoom in a little bit more. I want to be a little bit closer in. So I'm going to go from -5 to +5. And to change that window, I want to hit the window button and change my x minimum to -5 and my x maximum to +5. And what that's going to do is, on my x-axis, when I graph it, it's going to kind of zoom in from -5 to +5. Now that x scale of 1 just means that on the graph, my tick marks are going to be every 1. So if this is -5, that's -4, -3, -2, -1, 0, 1, 2, etc. And when you zoom in a little bit, you can see that it looks like the function crosses at -3, but it's not quite crossing at -2. It's a little to the left. It looks like it goes through 0, and it's a little to the right of +2. So I'm guessing that -3 and 0 are going to be good solutions. Now, there's a quick way to trace on your function, and then just type in, like, if I think -3 is a solution, after I hit trace, if I type -3, enter, it's going to take me to the spot on the function where x is equal to -3. And if it is, in fact, a 0, it's going to give me a point on the function of -3, 0. So I can see that that is a solution, or that is a root for this function. And I can just show that -2 is not by typing -2. It's kind of close to -2, and you can see that I'm not at -2, 0, I'm up a little bit. Okay, we said 0 was 1, so if I type 0, enter, 0, 0 works. That is a root, but 2 point something is not. So we know 2 roots that we could very easily use synthetic division with. So that's exactly what we're going to do. We're going to come over after we found that x is equal to 0 and -3. We know that those are 2 of the roots. We're going to kind of come back to those in a minute. You might want to highlight them on your paper. But we are going to use both of them synthetically. Now remember, I'm not going to go through a whole lot of the steps with synthetic division. You should be getting pretty good at it by now. But I do want to remind you to do your countdown. 4, 3, 2, 1. We're missing the constant term, which is why there is a 0 at the end here. You must have all of the parts, all of the terms from the largest exponent down to the constant represented in your synthetic division. Now we'll start by dividing by 0, and dividing by 0 is actually pretty easy because once you bring down the 1, every time you multiply 0 times something you get 0. So it's 3 plus 0, multiply all the way down till you get to the end, and 0 plus 0 gives us a remainder of 0. Remember that this remainder of 0 lets us know that we got this right. It is a root if you get a remainder of 0 when you use synthetic division. Now, the second thing I want you to remember after your countdown and how to do synthetic division is that we want to build our second synthetic division off of the first one. So once we get our results of 1, 3, -5, -15, not including the remainder, we want to build our second synthetic division using -3 into the result. So bring down the 1, multiply, add, multiply, add, multiply, and we get another remainder of 0. Now, if you start with a 4th degree and you do synthetic division 2 times, your result is going to be a quadratic because each time you do synthetic division, the degree goes down by 1. So we went from a 4th degree to a 3rd degree to a quadratic, a 2nd degree. And this one's going to be x squared plus 0x minus 5, which simplifies to be x squared minus 5. Now, when you set this equal to 0, I'm going to do it over here. You could use the quadratic formula here, but it's going to take you a little bit more time. Here is an appropriate place to use what we call the square root method, where you add 5 to both sides, and then you take the square root of both sides, but you do have to remember with the square root method that there are 2 solutions, a positive and a negative solution. So we have positive and negative root 5, and root 5 does not simplify. Now, if we want to know all of the roots of this polynomial function, we're going to list all of them out. We found 2 of them using our calculator. We found 2 roots, 0 and -3 using our calculator, and we found 2 more using synthetic division. I'm sorry, synthetic division and dealing with the resulting quadratic. And you want to list all of those as your final answer if you're asked to find the roots, not just the last one. A lot of students think, oh, here's my answer. This is what I finally ended up with. But don't forget, you already started with 2 that you found in your calculator, and you're just adding 2 more. For a 4th degree polynomial, you should have 4 roots. All right, as we work through some of these, you'll notice that I'll talk and then I'll kind of just speed up the tape so that the video doesn't take too long. If you want to try one of these on your own, it's not a bad idea to pause the video and try it and see if you can get it right. I'm going to clear out this function in my calculator and type in the new function for my second example. All right, so it looks like I've got a 0 or a root at -3, so let me test that out by tracing and typing -3, and yep, I got one at -3. You can see up here I've already kind of listed it out. I'm not sure about this one. It's in the middle somewhere, so it's probably going to be or end up being irrational. Now this guy, it looks like it bounces off right here, but if you kind of get close, it actually dips below right here. So we've got a root at 1, and then another root just a little bit to the right of 1. We don't know what that other root is, so we're going to have to use our tools, our synthetic division, dealing with the quadratic to get there. So next step after we find 2 good ones that we know are good, we know that x equals -3 and 1 are good. the next step is going to be to use synthetic division. Don't forget your countdown and just be careful along the way. All right, so it looks like this is going to end up being another one that does not require the quadratic formula, though you could use it where a is 1, b is 0, and c is -2. We're going to use the square root method again. We're going to add 2 to both sides, and then take the square root of both sides, positive or negative root 2. So, so when I'm listing out my roots, I want to list out the 2 that I found with my calculator. Those count. And also the 2 that I got with the quadratic, from the quadratic. And that was root 2 and negative root 2. I should have 4 separate roots using this method. So again, use my calculator to find 2 good ones. Use synthetic division with those 2 good ones to get the quartic down to a quadratic, then solve the quadratic to get the 2 remaining. We've got another one. Let's get this in our calculator first. So I'll clear what's here and start entering it in. Looks like it goes through at 3, so I know that one of my solutions is going to be x equals 3. The other 2 are kind of a mystery at this point, so I'll tuck away that one for later and also use it in synthetic division. We have a resulting quadratic of 4x squared minus 4x minus 1. I only had to do synthetic division one time this time because I knew that 3 was good, and I started with a cubic. So after using synthetic division one time, I go from the cubic to the quadratic. We can see here that we are going to have to use probably the quadratic formula. We could try to factor it. It's probably not going to factor. So here we got a is 4, b is -4, and c is -1. All right, so we need to write our final answer. So what are all of the roots? Well, the first root we found with our graphing calculator is +3. The second, we had to use synthetic division and deal with the quadratic to get 1/2 plus root 2 over 2 and 1/2 minus root 2 over 2. And this would be our final set of roots, all 3 of them, 2 irrational, 1 rational. And I'll note here, and we'll talk about this later, that the irrational roots always come in pairs, in part because of the way that we find them with the quadratic formula. We've always got the plus or the minus. And the other methods as well, you end up with a positive and a negative. They just tend to come in, or they always come in pairs. Irrational roots you'll find also come in pairs. Let's look at another example. We are asked to find all of the zeros. Again, we're going to use our calculator first to find at least one that is decent. It looks like it kind of bounces here at 4, but because I can't find the other one, this is going to be a fraction. I'm going to go ahead and just use the 4 one time and see if it occurs again as a second solution. So we'll come over here now that we've seen the graph and say we know that x equals 4 at least one time. It might be a double root. I didn't zoom in on the graph to see, but it looked like it might have bounced off, and we might end up with another root of 4 in a little bit. So we'll take that and use synthetic division. Right, we have a quadratic now of 3x squared minus 10x minus 8. Remember that you could try to factor this. It might be factorable, but you can always go back and use the quadratic formula. Even if it is factorable, the quadratic formula will work. So some students just start using the quadratic formula every time if they get good at it, if they like it as a method. So think back a minute ago, we said that maybe that 4 was a root twice. And what happened is this quadratic actually was factorable. And if you like to factor, you would have been able to factor it maybe a little bit quicker than dealing with this quadratic, or at least it would have taken as much room. If you prefer the quadratic formula, we still can get to the same answer, but what happens is if this discriminant is a perfect square, you're going to end up with something that you should be able to simplify. So I can actually add or subtract these two fractions together to get two answers. When I simplified 10/6 to 5/3 and 14/6 to 7/3, and I can actually add them together to get 12/3, which is 4. And I can subtract them to get -2/3. So what happened is my prediction was right. If I'm listing out my solutions, 4 was a solution twice. It turned out to actually be a bounce on the graph. And then -2/3 is another root. Now, with questions like this, there are other ways that we could have accomplished the same answer. And I don't want you to think that you have to use this method every time, but this is kind of like this works every time, right? For one thing, this is factorable, so we could have factored it to get 4 and -2/3. Also, if we did know that 4 was a double root, we could have used synthetic division again, and instead of dealing with a quadratic, we would have only had to deal with a linear equation, which is much easier to solve. So I kind of want to mention that to you. If you want to kind of play around, as long as the synthetic division works, you can kind of use it all the way down until you have a constant. I mean, until you have a remainder of 0, I guess, for at the end. I mean, it just kind of keeps working for all of these roots. I could use synthetic division. But what we're talking about today is something that no matter what this looks like, you have learned how to deal with quadratics that will get you the solution, even if it takes you a long way to get somewhere where you maybe could have done it a little faster if you'd thought about it. Final question today, we'll try to speed through this one. All right, so it looks like we have some potential roots here. Let's hit trace. I'm seeing -3 over here. Check that out, hit trace -3. I do see that works. Looks like this might be 0. I could zoom in to see it a little closer, but if I just type 0 when I've got trace on, I see that it's not actually going through at 0, 0. It's going through at 0, 3. So this ends up being somewhere between 0 and 1, and it looks like this one over here is somewhere between 1, 2, 3, and 4. So I know that -3 is good, but I don't know about the other two. So I'm just going to use -3, and I got that from my calculator. So our final solutions are -3, 2 plus √3, and 2 minus √3. We got those by finding a root of -3 in our calculator, using that root in synthetic division to get a quadratic, solving that quadratic using the quadratic formula, being careful to put everything in parentheses that we're substituting in, and simplifying it down to two fractions. I did have to deal with the square root of 12, which is 2√3, and then simplify those two fractions to get my simplified form here. Well, that may seem like a lot, but when you start practicing them, kind of start speeding up once you get the technique down. Hope that the video made sense. If you have questions, I'm glad to help you in class.